So I'll probably start in a minute. Okay, alright, so I'm Janzen, and I will be presenting the numerical methods section of the revision seminar. I'm just the presenter. These slides were made by the glorious Gerald Huang, so thank you for that, Gerald. I mean, like, look at these. There's like a progress bar at the bottom. It's really good. Okay, yeah, so today we'll start off with linear systems, then we'll go on to least squares, polynomial interpolation, nonlinear equations, numerical differentiation, integration, ODEs, and PDEs. Yep. So linear systems. Alright, so yeah, basically if the leading principal submatrices are non-singular or invertible, then the matrix can be factorized into unit, lower triangular, and upper triangular matrices, so L and U. A leading principal submatrix, AK, is a submatrix with only the first k rows and k columns remaining, so these principal submatrices would be square. Unit lower triangular matrix. For a unit lower triangular matrix, the main diagonal consists of 1, whereas the elements above the main diagonal are 0, and the elements below the main diagonal are non-zero. And yeah, so we can't have multiple LU combinations. If the factorization exists, it's unique, and the cost of LU factorization is to the power of 3. Alright, so the effects of permutation matrix. So adding a permutation matrix can rearrange the rows and columns to make the matrix LU factorizable. In the permutation matrix P, only one element in each column and row has a value of 1, whereas the other elements have a value of 0. So the order you multiply the matrices changes how P affects the matrix A. So the product PA would reorder the rows, while the product AP would reorder the columns. So by reordering the rows, we do not change the solution of the linear system. An example of this would be row reordering with Gaussian elimination, where we want to simplify the solving process. However, if we reorder the columns, the solution will change, so be wary. Yeah, so solving linear systems using LU factorization. So the idea of this method is to solve two linear systems instead of solving one complex linear system that involves inverting the matrix, which can be annoying and computationally burdening. So the process starts by multiplying both sides of the system by P, as you can see here, PA, PB, and changing the PA to LU. We then solve PB and replace it with Z, with a vector Z, and we let UX, we let UX equal to Y, so the equation becomes Ly is equal to Z, and we solve Ly is equal to Z for Y using forward substitution, where we solve the elements of the vector Y from top to bottom. once we have the vector y, we will solve ux is equal to y, so the original substitution, and we do that through backwards substitution. This time we solve the elements of x from bottom to top. Yeah, so these are the computational complexities of the algorithms. When we add the complexities together, the ON squared accounts for the n squareds in the forward and the ON squared accounts for the n squareds in the forward and backward substitution. So we can just replace the n squared. They're basically ignored in the sum, in the total cost. Alright, Cholesky factorization. Yep, so the Cholesky factorization involves factorizing the matrix into R transpose R, where R transpose becomes a lower triangular reflection of the matrix R. The Cholesky factorization of a matrix exists if and only if the matrix A is positive definite, meaning that it only has positive eigenvalues. The added benefit of Cholesky factorization is also that we can store the matrix A in terms of two upward triangular matrices, which means that the basically storing the matrix A is going to be a lot more space efficient, because you're basically sort of storing half the amount of elements. And yeah, it has a cost of n cubed on 3 plus on squared, so roughly half of that of LU factorization. Bam. Yep, so solving linear systems using Cholesky factorization. We can also solve linear systems more efficiently via Cholesky factorization. And it's quite similar to solving with LU factorization, in that we solve two simpler linear systems via forward and backward substitution, instead of inverting the matrix. So as you can see here, we're solving, we're replacing Rx with Y. We're solving RTY is equal to B for Y, and then we're solving Rx is equal to Y for X. Yeah, and again, the the n squareds in the forward and backward substitution are accounted for in the ON squared here. So the total cost would just basically be the cost of the Cholesky factorization, which is which has the dominant terms. Alright, sparsity of a matrix. So the sparsity of a matrix defines how dense or sparse a matrix is, and essentially how space efficient its storage can be. The sparsity can be calculated using this expression here, dividing the non-zero elements over the total number of elements. The non-zero elements are usually given, whereas the total number of elements is calculated from the dimensions of the matrix. So you can see here, this is a question, the 2010 paper. It's really hard to see, but I'll zoom in. See, it says that the non-zero elements, so the blue dots, there are 154 of them in the matrix. And basically, and the total number of elements would be calculated by looking at the dimensions of the grid, which is 36 by 36. So you can see here in the you can see in the calculations here, it's just 154 divided by 36 squared, approximately 11.9%. Yeah. Alright, so the vector norm. Vector norms satisfy these properties here. To acquire the p-norm of a vector, we bring all the elements of the vector to the power of p, and then sum them and p-root the sum. So there are shortcuts for the more common ones, namely the 1 norm, 2 norm, and infinity norm. So the 1 norm of a vector is the sum of the absolute values of the elements. The 2 norm, also known as the magnitude of the vector, is basically the rooted square sum of the elements. So the reason why it is also equivalent to this expression here is because x transpose x is basically the dot product of the vector x and x, which is also the squared magnitude of the vector. So if you square root both sides, it becomes this equation here. Finally, the infinity norm of a vector is the element of the vector with the maximum absolute value. This is because when the elements are brought to the power of infinity, the element with the greatest magnitude dominates the whole expression. So, yeah. So not too bad. Matrix norms. So with vector norms, we also have matrix norms. The matrix norms share quite similar properties as well to the vector norms. And a matrix norm is said to be consistent if this condition is satisfied. Cool. Yep, so the p-norm of a matrix is given by the expression here, where the vector x is a non-zero eigenvector of the matrix. Again, you will probably only come across the 1, 2, and infinity matrix norms, in which there are also shortcuts that we can apply to calculate these norms. So the one norm of the matrix can be calculated by finding the maximum column sum. Basically, for each column, the absolute value, you absolute value the elements and sum them together, and the one norm will be the maximum of those sums. And yeah, so for the infinity norm of the matrix, it's the same thing as the one norm, except you're doing the rows. Yep, and finally for the two norm of the matrix, you find A transpose A and calculate the square root of the maximum eigenvalue of that matrix. Alright, condition number. Oops. A matrix is non-singular if and only if neither the determinant nor the eigenvalues are 0. Just a note. And the p-norm condition number of a matrix is the product of the matrix and the product of the p-norm of the matrix and the p-norm of the inverted matrix. And the condition number basically just defines how well it is, how accurate it will be, how accurate the result will be when the matrix is used in a calculation. Yep, so the two-norm condition number of a matrix is simply the absolute value of the largest element, the largest eigenvalue over the absolute value of the smallest eigenvalue of the matrix. The greater the condition number, the worse the matrix gets, and the matrix is considered ill-conditioned if it exceeds the reciprocal of epsilon, which is around 10 to the power of 16. And yeah. So this question asks us to find the condition number of the matrix A, and they do give us the norm of the matrix A and the inverted matrix A inverse. Even though they already give us the norm, usually if they don't specify the condition number, you just assume that it's a two-norm condition number, because 2 is just like the default norm for matrices and vertices. So hence, basically we just multiply these norms together, and we'll get 4.18 times 10 to the power of 4. So let A equal this matrix, A inverse equal this matrix, and we have to find the infinity condition number of the matrix A, which means we have to find the infinity norm of the matrix A and the inverse matrix A, inverse of matrix A. So to find the infinity norm of the matrix, we're using the rows, the maximum rows. So here, first row is 5, second row is 3, third row is 6, so we choose the third row as the sum of the absolute value sum of the third row for the infinity norm of the matrix A. And we do the same thing for the inverse A, and we'll get 4. So again, the infinity condition number of matrix A would just be the product of 6 and 4, which is 24. Yep. And we basically just do the same thing for K1, except for the columns. Okay, sensitivity of a linear system. These are the expressions for the absolute and relative errors of vectors and matrices. The sensitivity of a linear system is the relative error of the solution X, which is approximately the sum of the relative errors multiplied by the 2-norm condition number of the matrix. Again, if they don't specify it, just assume it's the 2-norm. Yep. If the relative errors of A and B are 0, then they are known exactly, and their values are going to be 100% accurate. If a matrix or vector is known to k significant figures, then the relative error is less than 0.5 times 10 to the power of minus k. If a matrix or vector is known to k decimal places, then their absolute value is less than 0.5 times 10 to the power of minus k. So the value of k is what we refer to as the confidence of the matrix or vector. And as a note, if the relative error is greater than 1, then there are no significant figures in this solution, and we are not confident at all with the solution. Okay, cool. So this question gives us a bunch of code, and we have to determine whether we have to determine the properties of the matrix A. Alright, so is A symmetric? So given that the matrix, the difference between the matrix A and its transpose is very close to 0, we can basically say that A is equal to A transpose, in which A is symmetric with rounding error. Is A positive definite? Because A is symmetric, then so A is symmetric, and the smallest eigenvalue was given to be around 4.5 times 10 to the power of minus 2, which is positive, which means all the eigenvalues will have to be positive, and hence the matrix is indeed positive definite. Calculate the 2-norm condition number. Oops. Yep, so we're just getting the maximum eigenvalue and the minimum eigenvalue, absolute valuing them, and putting them into this expression here. So it gives us 2 times 10 to the power of 6. And because these are already positive, the absolute values don't really do much. Okay, cool. They want us to find the relative error in the computed solution of X. So we use the so they give us that A and B are known to 6 significant figures. So we can say that the relative errors of A and B are less than or equal to 0.5 times 10 to the power minus 6. Using the condition number that we got earlier and rounding it off a bit, we can put all these values into this expression here, which gives us a relative error for X of 2, which is greater than 1, so there are no significant figures in the solution of X, and the solution is not very accurate at all. Alright, given the Cholesky factorization A is equal to R transpose R, explain how to solve the linear system. Yep, so this process again is quite similar to LU factorization, and how we can use LU factorization to solve linear systems. Yep, so we basically just replace A with R transpose R, and we substitute Rx with a vector Y. So we solve this equation for Y, and then we solve Rx is equal to Y, and we do that through forward and backward substitution respectively. And yeah, so they don't really ask for they asked for a qualitative explanation, so we don't really need to use maths here. Yep. So the second section, least squares and polynomial interpolation. So for least square problems, basically they involve finding a line or curve that passes through a set of data, such that the total error of the line or curve to the data points is minimized. So we can do this through the normal equation or QR factorization, which both have similar computational complexities. Right, so for the first method, for normal equations, we multiply both sides of the equation by AT, A transpose, making the matrix on the left side symmetric and positive definite, because A transpose A. And so we can now use Cholesky factorization or OU factorization, and it basically makes the whole solving process a lot simpler. So the main issue with this method is that it is quite bad for larger matrices A, because multiplying both sides by A transpose effectively squares the condition number of the matrix, greatly increasing its relative error. So you might have to check before you apply this method. Check the condition number. Alright, so for method 2, QR factorization, this method involves factorizing the matrix into an orthogonal and upper triangular matrix. Orthogonal matrices are matrices with orthonormal column vectors, so the columns of the matrix are unit vectors and orthogonal or perpendicular to each other. The main reason why we would want to do this is because the inverse of orthogonal matrices is the same as the transpose. So transposing a matrix is a lot more efficient than inverting it. And that's why QR factorization is also effective. Alright, so just a note, basically when we use QR factorization, we can also use QR factorization to solve linear systems in the same way as LU factorization and Cholesky factorization. So as for polynomial interpolation, the idea of polynomial interpolation is that we are creating a continuous polynomial based on a finite number of data points. So given, say, n number of data points, the polynomial would be of degree n minus 1. So we can create a polynomial by placing the n number of data points into a linear system, as shown here, and solving for the n coefficients of the polynomial. So here the coefficients are just a0 and a1, and there are 2 data points, so there are only 2 coefficients. And basically for a smaller n number, so number of data points, it's quite easy because we're basically just simultaneously solving 2 equations. But for larger n values, this isn't really, practical. So for larger n values, we can employ Lagrange form. So it's more accurate, and so the Lagrange polynomial is given by the expression here, in which the final polynomial can be evaluated by summing all the YL products. Alright, okay, so here's a question. So for a function f, the following data are known. What is the degree of the interpolating polynomial p for these data? Right. So this is the first question. So that since there are 4 data points, the degree of the polynomial would be n minus 1, so 3. And basically we just set up this, if we solve this through a linear equations, we basically just set up the general form of the polynomial as such, and solve for the coefficients by substituting values in. So based on these equations here, we can set up a matrix A that stores all these values, and basically it will be a linear system that we solve, and we can solve this through, say, Gaussian elimination, or we could apply the other factorization techniques that we learned earlier. But in this case, they asked us to use MATLAB, so yeah, we could just use the backslash symbol to do so. And yeah, it says here, backslash command to solve for the matrix A, and eventually we'll get this solution here for the polynomial. So in using the Lagrange form, we basically just, we just substitute the values in to get the L expressions, the 4 L expressions, and once we do so, oh no, give me a second. So we had 4L expressions, and we're summing them together. We're summing the products of them with their the corresponding F expressions, F values, and in simplifying the expression, we'll get a similar degree 3 polynomial as we did for the linear, for when we use the linear system to solve for the polynomial, except this will be a lot more accurate. Yeah, so the use of Lagrange polynomials is quite effective, but there is still some polynomial error associated with the algorithm, namely here. This expression here calculates the absolute polynomial error in the interpolation process, and basically we can reduce the interpolation error by reducing the product of these terms. So the idea of that, idea of reducing the error is, I guess, the whole thing for, the goal of reducing the error is the whole idea of the Chebyshev points. So the Chebyshev nodes or Chebyshev points represent the optimal xj values, such that this expression here and subsequently the interpolation error is minimized. For an arbitrary interval AB, we can evaluate the xj values via this expression here, where the tj is represented by this cosine expression. And yeah, so I believe the Chebyshev nodes aim to minimize the oscillations near the edges of the interval, but I don't think that's really too relevant. But yeah, it's just this formula really. Cool. Part 3, nonlinear equations. Yep, so many problems in engineering are nonlinear, but we may still want to determine the existence or uniqueness of its solution. However, due to their non-linearity, we may need to employ non-traditional solving techniques to answer those questions. So nonlinear equations are usually in the form of this. So fx is equal to 0, and basically we're just solving for x. In other words, it can just be thought of as an equation, and we're just trying to find the x-intercepts. So if you see this notation, then the function f is continuous on the closed interval of AB and n times differentiable on the open interval AB. So for the intermediate value theorem, if fa times fb is strictly less than 0, then there exists at least one 0 on the open interval AB. If the derivative of a function is strictly positive or strictly negative for all values of x in a certain interval, then the function is monotonically increasing or decreasing on that interval. So if we combine both of these ideas together, basically we can conclude that, if if these two conditions are satisfied, then we can conclude that there exists only one unique root on that interval. Yep, so iterative methods for solving equations. So basically, because nonlinear equations can't really be solved through conventional techniques, we have to employ techniques such as we have to employ iterative techniques that use approximations that converge to the actual value. So most of the techniques learned in this course rely on iteration, in which we select an initial value and use it to iteratively get closer to the actual value. The idea is that after a certain number of iterations, we will have converged to the actual answer with an adequate level of accuracy. Usually they give us, the question will tell you to what decimal places or figures they want the answer to be. Yeah, so the order of convergence of a method is the largest value v, such that the limit of this fraction is constant, and where beta here, the constant, is the asymptotic constant. And yeah, here, so the error ek is just given by this expression, which is basically just the absolute value of the the actual value here and the approximated here. Oh, sorry, the other way around. So this is the approximated and this is the actual value. Yeah. So the bisection method relies on the fact that fa multiplied by fb is less than 0. That expression here indicates that a root exists on the open interval of a and b. So for this method, we basically repeatedly investigate the midpoint of the interval and halve the interval by either decreasing the upper bound or increasing the lower bound of the interval, so depending on which of these two conditions are met. This method is quite simple but extremely tedious, and it takes a lot of iterations to get an accurate answer. So yeah, that's why the order of convergence of the bisection method is linear. So v is equal to 1. Yep, so this method involves rearranging the equation. So whichever nonlinear equation we get, we basically just rearrange it such that a single x variable is on the left of the expression and the rest of the equation is on the right. So for the single variable on the left, we change that to x subscript k plus 1, and the x variables on the right to x subscript k. And in doing so, we just iterate through, and eventually, the idea is that we eventually converge to the actual root. But depending on the way you set up the expression, the method may or may not converge to the correct value. So to determine whether the selected function g will result in convergence, we must absolute value the derivative of the function g. If the absolute value of the derivative is strictly less than 1, then we are Gucci. Otherwise, we basically have to just select another g expression. Similar to the bisection method, the fixed point iteration has a linear order of convergence, and this method can also take many iterations until it reaches an accurate solution. Alright, so for Newton's method. So Newton's method uses a rearranged version of the tangent formula here. And basically in rearranging it and replacing one of the x terms here with a subscript k plus 1, we can approximate the root of a function, a nonlinear equation. So Newton's method is great in that it usually converges towards the root at a much faster rate than the bisection and fixed point iteration methods, requiring fewer iterations. So doing this by hand is a lot quicker. However, you have to be cautious when selecting your initial value, because so we have to make sure that it lies on the same concave of the function or the equation as the solution. Otherwise, we'll end up getting further away instead of closer to the actual root value with each iteration. This method has an added level of complexity, so in that you have to compute the derivative of the function before using it. However, the method has a quadratic order of convergence, so it will converge to the correct value with fewer iterations. So the derivative isn't too big of an issue unless the equation is a really messy one. So differentiating it would be quite computationally intensive. But otherwise, it's not a big issue if you're doing it by hand and the equation is simple. Yep. So we can also employ Newton's method to solve questions such as these, where they ask us to find the cube root of a root of a value through approximation. Yep. So show that Newton's method can be written as that. Yep. So basically, we want to find a cube root, the cube root of a. So we assign a variable x to this value here. We cube both sides and rearrange the equation such that we have an equation and we equate it to 0. So the general form of a nonlinear equation. And we set f to this equation, this expression. Yeah, so we substitute x subscript k. We differentiate it, so we get 3x squared, and basically we're just substituting these expressions into the Newton's method, which will give us this expression here. We are separating the numerator, the terms in the numerator, and then factorizing the 1 and 3 out, and just adding the like terms together, namely the 3x minus x, and we'll get this expression, which is what they want. Okay, another question. Yep, so you are given that the function has a simple 0 at 6.443. If you use a starting value near 6.443, what is the expected order of convergence? Yeah, so as long as your starting value and your actual value, so the actual root is on the same, are on the same concave, then it's fine. So the expected order of convergence will be 2. Yeah. Alright, so for the secant method, the secant method is actually quite similar to Newton's method. The only difference is that we are replacing f dash x with this expression here. So this is sort of like the gradient formula. So yep, so basically this expression has no derivatives, and we're changing the f dash x in the Newton's method with this expression, which gives us the expression in red. Yeah, so this, however, so this means that we don't have to compute the derivative of the function, but we do have to use 2 starting points. This method is a tiny bit simpler than Newton's method, and so it has an order of convergence of around, well, this equates to around 1.62-ish, which is, yeah, slightly less than Newton's method. Alright, so part 4. We're actually going really quickly. If you guys have any questions, do my best to answer them. Otherwise, let's just continue. So the Taylor series approximates a non-polynomial function as a polynomial. Below are some examples of common Taylor series. So this is the Taylor series for the exponent, so the Euler's number, and the ln expression here. It's not too bad. So the Taylor series requires the non-polynomial function to be continuous on the closed interval, and n+1 times differentiable on the open interval. Here we are substituting x plus h into the general expression of the Taylor series, in which the remainder, or error, will be defined by this expression here. Usually we can express this remainder via big O notation, so you don't really have to, write this expression. However, if they specifically ask for you to do so, I guess you can't just write with the big O notation. So forward difference approximation. So the forward difference approximation allows us to evaluate values of f dash given values of f via the following expression. So this expression is derived from the first two terms of the Taylor series for fx plus h. So basically this this expression here, and basically once you use these few terms here and rearrange them, these few terms here rather, the fx and f dash xh and you equate that to fx plus h, and once you rearrange them you get something like this. The round-off error is given by epsilon on h, and the truncation error is given by OH. So I guess the truncation error represents the parts of the Taylor series that you are ignoring. So the OH, the big O notation, the expression represented by the big O notation. And so basically if h approaches infinity, the round-off error approaches 0, but the truncation error approaches infinity, which is bad. Alright, so the central difference approximation here allows us to evaluate values of f dash and f dash dash, given values of f, via the following expression here. The expression here only represents the approximation for the double derivative. If we wanted the single derivative central difference approximation, basically we just use the same Taylor series, except we just ignore one of the terms. We ignore this term here to get the first order central difference approximation equation. The truncation error for central difference approximation for both single and double derivatives are OH squared. This is in comparison to the truncation error for the forward difference approximation of OH. Cool. So for the idea of quadrature rules is to approximate an integral by applying weighted sums of function values. Depending on the rule, the weights will differ. Ideally we want the approximation or quadrature error to approach 0 as n, the number of subintervals, increases. So for the sake of convergence. So basically we just want our we want our approximation to be accurate as the number of subintervals increase. So these are the three quadrature rules taught in the course: trapezoidal, Simpsons, Gauss-Lejeune. So as the name suggests, the trapezoidal rule approximates the integral using n number of trapeziums. On the interval AB, the height h, or the step size, will be defined as such. To get xj, we basically just split the so to get xj, we split the interval into n plus 1 separate points, inclusive of the values of the bounds a and b. And we substitute those xj values into the function and sum them up with their respective weights. The weights for the trapezoidal rule are h12 for the first and last element, and h for the other elements. So this is quite one of the simpler quadrature rules, except because it's using trapezoids to approximate the area, it's not going to be super accurate. And so this is the error associated with using the trapezoidal rule. So the Simpsons rule approximates the integral using a series of parabolas and sums the area underneath the parabolas. Since the rule approximates integrals using parabolas, if the function that you're trying to approximate is a parabola, then the approximation would be very accurate. On the interval a and b, the height or step size will be defined as such, so it's quite similar to it is the same as the trapezoidal rule. And again, to get the xj values, we split the interval, so the a and b interval, into n plus 1 separate points, inclusive of the values of a and b. The weights of the Simpsons rule is a bit more complicated in that the first and last elements have weights of h13, whereas the other elements have alternating weights of 4h13 and 2h13. So if n were equal to 4, then the weights inside the brackets here would be 4, 2, 4, or rather like 1, 4, 2, 4, 1. If n were equal to 6, then the weights inside the brackets would be 1, 4, 2, 4, 2, 4, 1. So it's just that the non-first and last elements will follow this 4, 2, 4, 2 pattern. And it has to be an even number, otherwise the pattern just won't work. Cool. So in comparison to the trapezoidal rule, the error of Simpson's rule is much lower for greater values of n, meaning that the approximation converges faster towards the actual integrals. So you can see here this is n to the power of minus 4, whereas for the trapezoidal rule it was n to the power of minus 2. Cool. For the Gauss-Lejeune rule, the xj values are not separated by equal intervals, in which they are zeros of the Lejeune polynomial of degree n on this interval here. So this rule relies on the bounds of the integral being minus 1 and 1. So we do have to do something about that, which we will discuss in a bit. So these are the... despite the complexity of this algorithm, the error of the Gauss-Lejeune rule is quite significantly lower than the other rules. As you can see here, it's 2n factorial instead of being a power. So these are the assumptions for each of the quadrature rules. Basically the open and closed interval conditions that we talked about earlier. So quadratures assume integrand f is sufficiently smooth, just basically that there are no sudden spikes in the equation, which would be quite difficult to approximate. Change of variables. So this is what I was talking about when I said that the bounds of the integral had to be 1 and minus 1 for Gauss-Lejean's rule to be, I guess, viable. So changing the variables allow us to transform any arbitrary interval AB into minus 1 and 1. Thus making the integrating function applicable for the Gauss-Lejean rule. Using the integral bounds, you can substitute this expression for all the x values in the function. So basically, just we have the fx expression here, and we're substituting all the x variables with this expression. So once we have done that, we can use the Gauss-Lejean rule. Tips for estimating difficult integrals. So if your integrating interval is not on minus 1 and 1, basically we can apply the change of variables to use Gauss-Lejean's rule. If there is a discontinuity on in the derivative, we would have to split the integral at the discontinuity and evaluate the separate integrals and sum them together to get the integral of the whole expression. For high oscillatory functions, basically, you just have to apply a special analytic method. There's no way around it, but they probably won't give you a question where the curve is highly oscillating or has high oscillations. And yes, it's the same thing for the narrow spikes as well. Basically, the quadratures assume that these two situations don't happen. Cool. ODEs, part 5. Yep, so ordinary differential equations, or ODEs, are equations that involve derivatives. So the order of the differential equation simply denotes the highest order derivative within the ODE. So for this ODE here, the highest order derivative would be 1, so this would be a first order differential equation. So for a first order differential equation, the highest order derivative in the equation is 1 if it is an initial value problem, or IVP. Then the initial conditions of the equation are involved. So it's quite simple, really. If they don't give us the initial conditions, then usually just sort of not incorporate it into your answer. But yeah, cool. If the function and y derivative of the function are continuous and bounded over a time interval, then the initial value problem will only have one unique solution. So this is basically what this theorem is talking about. Euler's method. Alright, so while not the most computationally efficient, Euler's method is one of the simpler methods to approximate the first order differential equation with a given initial value. So Euler's method relies on approximating the integral using a series of rectangles. So Euler's method has two main versions, namely the explicit and implicit or indirect Euler method. The distinction between the versions being the y values we choose for the rectangles. So I'll just bring up these notes here. So this is the explicit Euler method, whereas this is the implicit Euler method, and you can see that the rectangles used to approximate the integral differ slightly. So as you can see here, the rectangle here relies on the second point, whereas the rectangles here rely on the first point as the heights of the rectangle. So for positive gradients, the explicit Euler method will be the approximation of the from the explicit Euler method will be greater than the actual value. But for negative gradients, the approximation will be less than the actual value, which you can kind of see here. The approximation is slightly greater, the approximation here is slightly less. And the converse is true for the implicit Euler method. Yep. So the expression here represents the explicit Euler method, but if we want the expression for the implicit Euler method, we just need to change the n subscripts here to n plus 1. So there's not too much difference in the two methods. Yeah, and as a final note, if we want to increase the accuracy of the approximation, we want to decrease the step size h and in turn increase the number of points n, which is, yeah. So for systems of first order ODEs, we simply replace the x values with a vector x, as you can see here. Otherwise, it's quite similar to solving single first order ODEs. So here's an example question from the 2010 paper. Yep. They want us to reformulate the IPP as a system of first order differential equations. Okay, cool. Yep, so we basically just define a x vector as such, and say that the x1 is equal to y, x2 is equal to y dash, and x3 is equal to y double dash. Yeah, and basically we just want to equate the x dash terms. So as you can see here, we basically want to equate the x dash terms with expressions involving x1, x2, and x3. So x1 dash is equal to x2, x2 dash is equal to x3, and x3 dash is equal to y triple dash, which is also equal to this expression here, which is yeah, just an expression of x1s and 2s and t's, which are fine. Yep, and basically for this step here, we're just replacing the y triple dash with the expression it represents, and yep, and we're also using the initial conditions that they gave us and putting it in the initial condition vector x0 as such, and this is your final answer. Alright, the Runge-Kutta method. So this is the explicit Runge-Kutta method, which involves solving the coefficients for each iteration. So yeah, solving the coefficients for each iteration using expressions that you found from the last iteration. So again, this is a iterative process. Yeah, so the second and fourth stage Runge-Kutta method rely on these expressions. But if you want a V-stage Runge-Kutta method, you would have to do some funky matrix magic. But otherwise, you can just rely on these equations here. I'll just show. Yep, so regarding the matrix magic, basically you just have to set up a grid as such and solve for the zeta values, and eventually you get the individual expressions or the general expressions for the V-stage Runge-Kutta method. But they should only give you questions regarding the 2 and 4 stage Runge-Kutta method, so remembering these two expressions is sufficient. Yep, find the solution of the initial value problem using Euler method. Okay, so they give us this expression here. F is equal to 3y plus 3t. They also give us the initial values. So we can say that y0 is 1 and t0 is obviously 0. Yep. They want us to find y 0.2. So we're just using the equation, the explicit Euler method equation, and we're substituting the initial values to get the y value for a step size of 0.2, which is 1.6. Yeah. Okay, using the fourth order Runge-Kutta method. So this is the general expression for the Runge-Kutta method for a step size of 0.2. And yeah, we're relying on the initial values. For t0 is equal to 0 and y0 is equal to 1. And we're just using these equations here to determine the k coefficients. And yeah, these two will give us the values of the k coefficients. Cool. Yeah. Basically, we're just substituting the k coefficients into the expression here, and we're getting this value. So as you can see, even with one iteration, with a step size of 0.2, the resulted y value, the approximated value, is a lot higher than 1.6, as we got from the Euler method, meaning that the Runge-Kutta method is a lot more accurate, and it converges to the actual value a lot faster than the Euler method. And I guess we can attribute this to the high complexity of the Runge-Kutta method. Yep, so yeah, so again, this is the implicit Euler method, as we discussed, where we replace the n subscripts here with n plus 1. This is the Taylor method, trapezoidal method. So for the Hoynes method, we're getting the implicit Euler method and the explicit Euler method earlier, and we're averaging them, resulting in this expression here. So individually, they approximate the Euler and the implicit Euler and explicit Euler methods approximate the integral using rectangles, but by averaging them, Hoynes method approximates the integral using trapeziums, similar to the trapezoidal method, sort of. And I'll just show an image here. So this is the explicit Euler method. This is the implicit Euler method, and in averaging them, we'll get something like this. So they are no longer rectangles, they are trapeziums. And yeah, it's neat, quite neat. Right, final topic, PDEs. PDEs are, so partial differential equations, or PDEs, are basically just ODEs, but with multiple variables. So as a result of using multiple variables, PDEs will have partial derivatives in their equations. For MATH2089, the highest PDE that you will probably come across is will probably be order 2, with a maximum of 2 variables. So it shouldn't be too complex. So to approximate the partial derivatives, you can employ the finite difference methods, namely the forward, backward, and central approximation. Sorry, forward, backward, central difference approximation methods. Yeah. So we can just use the same methods as we did for the single variable derivatives. The only difference is that you have to change the variables, and instead of writing d, you have to use this symbol here for partial derivatives. And so this equation here is the central difference approximation for single partial derivatives. So the general form of the PDE is represented by this expression here, with varying coefficients of A, B, and C. So this will be the general expression that you'll come across in the course. And depending on the variables A, B, and C, the PDE will either be elliptic, parabolic, or hyperbolic. So these are just relying on the determinant of A, B, and C. So for elliptic PDEs, we are dividing the x and y intervals by m plus 1 and n plus 1 and n plus 1 equal length subintervals. And that will give us the step size values. So for each point on the subinterval, we are using the central difference approximation to approximate the partial derivatives. Since these partial derivatives are of second order, we will be using the second order central difference approximations. So there's 2 here, so we have to employ the second order central difference approximations for the 2 partial derivatives. We then substitute the approximated partial derivatives into the original PDE. So basically for elliptic PDEs, we will have this expression and this expression. So basically we can just equate these 2 expressions and rearrange the values to get the expression in the form that they want us. So for parabolic PDEs, the explicit method to approximate parabolic PDEs, we are using both the forward and central difference approximations to approximate the derivatives. Since the time derivative is first order, so delta U and delta T, we will use the first order forward difference approximation. But for the since the space derivative is of second order, we will be using the second order central difference approximation as shown here. I'm not sure if they mark you on these squiggly equal signs, the approximated equal signs, but I think it's good to make that a habit. Again, we just substitute these 2 values into the original PDE and rearrange the expressions to get whatever form they want us to have the expression in. And basically after doing so, we will get an iterative equation as shown here. For the implicit or indirect method to approximate parabolic PDEs, instead of using first order forward difference approximation, we are using the first order backward difference approximation. So backward difference approximation, the difference is just that, just the subscripts are slightly different. However, they just employ they do employ the same method, in that you have to substitute these expressions back into the original PDE, rearrange it, and get into this sort of form. So as you can see here, the L plus 1 expressions on the left, whereas the L expressions, the U superscript L is isolated on the right. So for the explicit, the U superscript L plus 1 was isolated instead. Finally, for the Crank-Nicholson method, it combines the explicit and implicit methods for the parabolic PDEs and averages them, which is sort of analogous to how Hoyne's method averages the explicit and implicit Euler methods, which results in a more complex method, but also a more accurate solution. So yeah, this equation is quite hard to remember. Yeah, so the implicit and Crank-Nicholson method both benefit from being always stable, so unconditionally stable, which is nice. So for the hyperbolic PDEs, they are quite similar to elliptic PDEs in that we are using second order central difference approximations to approximate both second order partial derivatives. I guess the only difference here would be the fact that instead of t it was y for the earlier example. So it's one less thing to remember, one less set of equations to remember. Yep, so similarly we substitute the approximated partial derivatives into the original PDE, in which we'll get a so after rearranging it we will get an iterative equation for the PDE. So just a note, because it's iterative, we're basically discretizing the equation, so it's no longer continuous. Final problem. A lot of the numerical method past papers have PDEs as the final problem, so yeah, I guess this is quite important to get a grasp of. So yeah, so this question requires us to approximate a parabolic PDE via the explicit method. So it's a parabolic because it's one of the partial derivatives here is of first order. And yeah, so they also want us to so we know that it's explicit because they asked us to use, we know that they want us to use the explicit method because they asked us to use forward time difference approximation and central space difference approximation instead of the backwards version. And yeah, so we approximate the time derivative via the first order difference approximation, which gives us this expression here. Then we approximate the space partial derivative via the second order central difference approximation. And once we get these two expressions, again we're just substituting it back into the original PDE. Since this PDE just equates these two partial derivatives, we can just equate these two expressions here, these discretized expressions here, and rearrange them. Oh no, right, okay. Yep, so once we rearrange them, we replace the step sizes with delta t fractions, and yeah, that's basically it. And yeah, this is basically what the question will ask for. And cool. I mean, it's basically done, the revision seminar. So if you guys have any specific questions, go ahead and ask them. I don't think the screen is frozen, but it's not frozen on my end. Again, just like to thank Gerald for making these beautiful slides. And they're great, really. Yeah, it was fun. Yeah, so if anyone has any questions, you might want to ask now. Week 9 quiz. Alright, sorry, I'm just trying to find some past papers. I don't have your week 9 quiz, unfortunately. Oh gee. Can you tell me what type of question your week 9 quiz contains? And I will do my utmost. Pretty much a bunch of theory, PDs. Okay, I can go through some past papers involving PDE questions. However, I can't really write on my laptop, otherwise it will lag. Past papers. Yeah, I found the past paper questions more useful when studying for my finals than the tutorial questions. So, not sure how many the lecturers supplied you guys with in terms of the past papers, but yeah, try practice as much as you can. Okay. Did they give you solutions for the past papers? Never going to lie. Never seen a past paper for numerical. I'm sure someone will post the solutions. The past papers in the group chat. Hopefully, can we have some? Can we have the past paper solutions? Sure. I can send it to Gerald, and perhaps he could supply you guys with the past papers. I don't know. I got a lot. I'm not sure how I got them, but I ended up with a lot of past papers. Some of them had solutions, some of them didn't. So, yeah. They gave us the past papers, but not the solutions. Yeah. I mean, yeah. Okay, I guess I'll just go through the questions using the solutions, because I can't really write. Alright, I mean, do you guys have any specific questions you want me to do? Just explain the... Yeah, we didn't really anticipate finishing in the 1 hour, but we did. Okay, I'll just go through the solutions. So basically, the third question, question 3, what additional information is needed to complete these, completely specify the problem? So for most PDEs, you will require the domains, the time and space domains, time domains and space domains, and as well as the initial conditions and the boundary conditions. Yeah, so they give us the conditions, and yeah. Second question, what is the steady state version of the fixed second law? Yeah, so this the steady state version basically, as t goes towards infinity, and when that occurs, basically t won't have an effect on the PDE anymore, which results in this expression here. So the original PDE looked, where is it? Yep, it looked something like this, and because delta c on delta t is equal to 0, we can the steady state expression would just basically be these two expressions, or rather these two terms, being equated to 0. At the point x, I, y, j, and time t subscript l plus 1 give us a backward difference approximation. Yeah, well, it's really just substituting the I and j and l plus 1 subscripts and superscripts into the backward backward approximation equations. And here, instead of writing the step size, the person who wrote the solutions used the deltas, which works as well. So yeah, just make sure that the I guess that the superscripts and subscripts are don't get mixed up with each other. Okay, so they want a central difference approximation, so question D. And they want us to use the central difference approximation to approximate the second order partial derivatives. Yep, so again, basically just substituting the I, j, and L plus 1 superscripts and subscripts into the central difference approximation equations. And yeah, the difference. Oh yeah, so the slight difference in this is that these two expressions is that the subscripts change slightly, because this is I minus 1, this is j minus 1, because this is the partial derivative with respect to the y, or the j component here. So it only affects the, yeah, so the when you're partially differentiating the expression for c with respects to x, you change the subscripts for I, but when you're partially differentiating with respects to y, you're changing the subscripts for j. And since t aren't involved in this expression, I guess this differentiating, the L plus 1 subscripts also, the L plus 1 superscripts also remain the same. Cool. Yep. Using the finite difference approximations from the previous two parts show that Fick's second law is approximated by this expression. Yeah. So they want us to express the partial derivative, the PDE, into a discretized form as such, and we have to find the alpha and beta coefficients. Yep. So when you're rearranging when you're substituting the approximated forms back into the original PDE, you ignore the big O notations as well. And yeah, so we're substituting this expression, and this expression without the OH squared and the OT notation. Sorry, the OT error, truncation error. And yeah, we're substituting them back into the original PDE, namely, where is it? This one here. So instead of writing these delta C on delta T, we substitute this expression. As for the other two second order partial derivatives, we substitute the discretized forms here. And yeah, so what they did in the solution, they multiplied both sides by delta T, and and they replaced the d delta T on h squareds with s. So effectively, this factor, we are factorizing the h squareds out from the right side, so we will get d on h squared. Then we multiply both sides by delta T, so we get a factor here, d delta T over h squared, and we are replacing that expression with s, creating this expression here. And yeah, so basically we'll get alpha and beta in terms of expressions involving s. Question F. Suppose that CUYT. Alright, so these are the boundary. So this is the boundary condition, this is the initial condition. Find the equation at the grid point x1. Yeah. So they give us these two conditions here, and we can use them to identify the to try to evaluate the unknowns in our approximated equation, and in doing so we can substitute x1 and y3, so the given values x1 and y3. Where is it? Yep. Oh yeah, sorry, x1 and y3 here. Yeah, okay, so that's what they did. So the boundary equation, the initial condition, they're substituting these values into the approximated form, and in doing so, they got that L is equal to 0. Oh, sorry. Where is it? Actually, this is quite confusing. They didn't seem to have. Oh, right. Okay, so I guess they're just instead of writing the. All right, so they're using the these values here as the values for the previous iteration to try to create the expression for the this iteration here. So is this an explicit method or implicit method? Briefly discuss the relative advantages and disadvantages. So explicit meaning that the method is direct, so it looks for like future iterations using previous iterations. For implicit methods, it's sort of indirect. So the disadvantages of implicit methods is that we need to solve linear systems to get the unknowns, but it's advantageous in that it's unconditionally stable. So there are no restrictions on the step sizes for the space and time domain. For the explicit method, we are solving the L plus 1 in terms of the unknown values of L for the values of C subscript L. But there are conditions, and therefore they're depending on the values of the step sizes, the method may or may not be stable. Okay, so we are given this matrix. We did do this question in the slides earlier, and we found that the sparsity was around 11.9. So again, they give us the non-zero elements and the dimensions of the matrix. They also want us, so someone wanted us to do some earlier middle exam questions. Alright, I can do that. Yeah, basically this is the end of the paper anyway. So these type of questions, it's really just substituting these values into the expressions and trying to find the values of that they want us to find. So namely answer 1, 2, 3. And we do have to try to recognize whether this will break the MATLAB. The code will break MATLAB in terms of whether it's too big or too small. Yeah, so given so x is 10 to the power of 200, and if we take it to the power of 3, it will be 600, but that is greater than the real max, which is 10 to the power of 308. So this will the MATLAB will output infinity, and that's the type of thing you have to, I guess, recognize when you're doing these type of questions. Again, so this is a vector -2, 0, and 2, and they are element. They're doing an element division. Yeah, so it results in this. But when you divide 0 by 0 in MATLAB, you get NaN. That's why. Yeah, you get something like this. But MATLAB can do complex arithmetic, so you would end up with I in the answer. Okay, x is equal to 0.1, h is equal to 10 to the power of minus 18. When you add them together, oh, okay, so this is like a conditional answer. It's either 1 or 0, false or true, true or false. Yeah. So epsilon is 10 to the power of minus 6. So we do have to consider whether h is big enough to be considered as, I guess, a number in the arithmetic process of MATLAB. And yeah, you do that by determining the absolute error of the number. So x, the absolute error of x is 0.1 times 10, so 0.1 times 2.2 times 10 to the power minus 16, so epsilon. And you get, yeah, 2.2 times 10 to the power minus 17. But that is, that causes h to basically be negligible. So this basically becomes x is equal to x, and this inequality results in a true output. Yeah, a lot of past papers also give us these type of questions. And in these type of questions, you basically just ignore the big O notation in trying to calculate how many flops a certain process will take. Okay, so estimate the size of a large linear system that can be solved in 1 minute on a 3 GHz quad-core computer, where each core can do 2 floating point operations per clock cycle. Assume that the coefficient matrix has no special structure. So because the coefficient matrix has no special structure, it means that Cholesky factorization may or may not work. So we do have to rely on LU factorization. So again, Cholesky factorization relies on the matrix being positive definite, which not all matrices are. Okay, so yep, so for LU factorization, the number of flops would be 2n to the power of 3 on 3. And yeah, 3 GHz quad computer, it just means that it has the capability of doing 3 times 2 to the power of 30, I think, times 4, because it's a quad-core computer, and then we have to multiply it by 2. So as you can see here, 3 times 10 to the power of 9, or 2 to the power of 30, times 4 times 2, because it can do 2 flops per clock cycle. Basically, you just determine the speed of the computer by multiplying all these values together, and you find that it can do 2.4 times 10 to the power of 10 flops per second in 1 minute. So basically, we just multiplying this by 60, we'll get 1.44 times 10 to the power of 12. So again, because the matrix has no special structure, we have to use LU factorization. And we are substituting we're trying to find the largest value of n, such that this LU factorization can be done in 1 minute. So we're equating the total number of flops per minute to the computational complexity of LU factorizing, isolating the n cubed, and then finding that, and solving for n, which reveals that it's 13,000, around 13,000. And we do have to round this value to make it an integer. But because some people can interpret gigahertz as 2 to the power of 30 instead of 10 to the power of 9, the exact value of n doesn't really matter too much. It just has to be around the same as what the I guess lecturers wrote down as the correct answer. if multiplying two n by n matrices takes 12 seconds, estimate how long it will take to solve an n by n symmetric positive definite linear system. Okay, so positive definite linear system, and it's also symmetric. Cholesky factorization, basically. And that is that has n cubed on 3. Okay, so multiplying two n by n matrices takes 12 seconds, and here they give us that the number of flops that it takes to multiply two matrices together is 2n to the power of 3, where the matrix is n by n. Yep, so after multiplying the matrices, we then have to solve it, and we can solve it through Cholesky factorization because it's positive definite. And here, so 2n to the power of 3, and that takes 12 seconds. Yeah, so what they did here is that they used the Cholesky factorization, and they made it so that n cubed, they did some factorizing to make it so that 2n cubed is inside the bracket, so you can directly substitute 12 in. Otherwise, you can just, for this expression, divide it by 2 and then cube it to find n, and then substitute it back in to the complexity of Cholesky factorization. And yeah, 2 seconds. Okay, so the coefficient matrix A and the right-hand side vector B are known to 8 significant figures. Cool. What is the condition number of Ka? So for this question, because they don't give us a norm for the condition number, it doesn't matter too much. So you can just, because they also don't give us the norm for the matrices, matrix norms. So you can assume that they're all the same, and the condition number will just be a product of these two norms, as you can see here. Yep, it's just a product, and you get 4.18 times 10 to the power 4. How many significant figures are there in a computed solution to AX equal B? So to find this, we have to get the relative error of A and relative error of B, add them together, and then multiply it by the condition number that we just found. Yep, so that's what they did. The relative error, because they give us that those two, the matrix and the vector, are known to 8 significant figures, we can say that the relative error is going to be, for both of them, for the A and B, are going to be less than or equal to 0.5 times 10 to the power minus 8. 0.5 times 10 to the power minus 8. We add them together, and then we multiply it by the condition number, which gives us the relative error. So because this value here is less than 0.5 times 10 to the power minus 3, we can say that we expect at least 3 significant figures in the computed solution X. You want to find an intersection of the functions. A lot of MATLAB. Okay, yeah, so to find the computed solutions, to find the intersection of the functions, we are just equating these two function expressions together. And you can also, once you equate them together, you can also move one of the expressions to the other side so that one of the sides of the expression is equal to 0. As such, so f is equal to f1 minus f2, and you'll get this expression here, and you just equate it to 0. Yeah, easy marks. The second part of the question wants you to define the f expression in MATLAB. Make sure that you include the periods to indicate that you're doing element derivatives, so period, arrow 2. So yeah, secant method. So these are the absolute values of the errors for the secant method. Is the method converging, and what is the order of convergence? So so superlinear just refers to an order of convergence that is between linear and quadratic. So for the secant method, it was around 1.618. So the order of convergence of the secant method is 1.618. Okay, so for the first part of the question, the error is equal to this, and basically we're just looking at the way the errors change, basically. So okay, ek plus 1 on ek. So the this results in a so it's converging towards 0. So v will definitely be greater than 1. And for this one, this expression, you can see that it's sort of it's not converging. It's going to diverge to infinity. So it definitely has to be less than 2. So v is greater than 1 but less than 2. Is the method converging? The method does converge, but it converges between linear and quadratic, like we said. So the order of convergence is superlinear, and that's basically what they wrote. It's between 1 and 2. I guess you don't really need to remember the exact value of convergence. Second question. This is a least squared problem. No, it's not. Yes, it is. Alright, you are asked to approximate CT by the interpolating polynomial. What is the degree of the interpolating polynomial? So you just to find the degree, you look at the number of data points that they give you. So they give us 5 data points. So the degree of the polynomial would be 5 minus 1. Oops. Yep, so 5 data values, the polynomial would be n is equal to 4, so degree 4. Now, give 2 reasons why this is not a sensible approximation. Okay. Well, we can say that okay. I guess it's because as x approaches infinity, as t approaches infinity, it's supposed to the expression is supposed to converge to 0 or go towards 0, but it goes to infinity. But yeah, it's just too many curves used to approximate the data points, and that's what they basically said here. So from the plot, the interpolating polynomial is less than 1 for t is 1.8, which is not realistic, which also makes sense. So yeah, between these two points, the green curve is less than 0, and you can't have a negative concentration. As the chemical is being consumed, an approximation of the form is thought to be more appropriate. Give MATLAB commands, assuming that the data column. Alright, so they basically stored these values here in column vectors, tdat, and these values here in cdat, and you just have to use these column vectors to set up a linear system to solve, as shown here. Okay, so before doing that, however, you do have to so you do have to rearrange the equation, the exponential equation, such that it has the form, has a linear form of, log alpha minus beta t, except instead of writing log alpha, you just write alpha bar, so it does in a sort of linear form, and yeah, you place the column vectors into a matrix, a 2x5 matrix, and you solve for the value of x, and from the value of x you can determine the value of alpha and beta in MATLAB. You don't have to do it, you don't have to find the accurate values. Again, because we substituted log alpha for alpha bar, we do have to use the exponent function to calculate the actual values of alpha. Cool. Approximating the integral. Yep, so these are the formulas for the Simpson's rule and the trapezoidal rule. Use the table to in 2.1. Where is 2.1? Just to estimate this. Yep, so basically we're just using these values here to approximate the area underneath the curve. And because the values of t are separated by equal subintervals, or equal intervals, subintervals, so we can use Simpson's rule and trapezoidal rule. And in doing so, you basically just apply the values from the table and apply the weights corresponding to the equation using to get the approximated Simpson's rule. It's really just the formula here. Oh yeah, so the second part of the question was to estimate how much the error in Simpson's rule will decrease. So the Simpson's method has a error of n to the power minus 4, or h to the power 4, so we can just substitute the h value into, so we can use the we can determine the step value, so h, which is around 2, we can half, h is equal to 0.5, so we can substitute that into the oh to the power 4 expression, and yeah, basically the error will decrease by 1 in 16 every iteration. Can a Gauss-Lejeune rule be used to estimate the integral using just the data values in table 2.1? Alright, are not equally spaced, so this would require data values. Okay, that's fair enough. So the Gauss-Lejeune rule chooses optimal nodes and the corresponding weights. Yeah, because they only give us the data points. They only give us these data points. We don't know the values of the concentration function between these time. So we can't really choose any other points to approximate the integral with. That's why Gauss-Legeune's rule just won't work. I believe we have done this question in the we did this question in the slides. Basically just replacing the x dash elements of the x dash vector with expressions of x1, x2, x3, and write the MATLAB code. And then we're basically done with the numeric section. Do you guys have any other questions that you want me to do? Or do you guys want to call it? I mean, it has been 2 hours, so it's, fitting to end it here. Cheers for hoping you can go free. Thank you. Yeah. Basically, good luck for your 2089 endeavors. It's a fun course. It's just not structured well. Quite unfortunate, really. It's a waste of good content. But yeah, good luck for the finals. Thank you, Gerald, for letting me present and making these very nice lecture slides. I mean, they look proper. They look like proper lecture slides that you would find. Cool. Well, see you all perhaps next time. Has been fun. It's been a pleasure.